First, I want to thank everyone for being here. I want to thank my sponsors. Usually when I say this, it's just astronomers in the audience. The sponsors are actually here. So thank you. We've had a lot of astronomers doing chemistry and chemists doing astronomy. So I'm an astronomer doing chemistry who's going to pretend to be a planetary scientist right now. So off we go. So what you can't see here all that well, but we're actually at a new age. We're detecting planets around other stars. And actually this image, if you could actually see it, you're actually observing another planetary system with the planets rotating or orbiting around their star, which is insane where we are today, right? So what we want to know from the perspective of chemistry is what sets the composition of a planet at its birth, right? And what does that mean? Okay, that's the other question, right? Does the chemical composition we observe today, how does it relate to birth? And is a world like our own a preordained outcome? Is, when every planetary system is born, is there an Earth there? And does the Earth have the right stuff? And ultimately, of course, we want to know, is life present and how life could come? And I'm going to be very simple about this. I'm going to ask the question very directly, is carbon present on the surface of the planet? Elemental carbon, all right? And assume then that the Earth and the chemistry on the Earth can then do whatever it wants to make life. So it's a little bit different than asking about whether we're providing the amino acids and so on and so forth. Just another way of approaching it. So here's the planets in our solar system. So we have Jupiter, Saturn, Venus, Earth, Mars, Uranus, Neptune. Each of them actually has a chemical story to tell that relates to their origin. Can somebody name, what's their favorite planet up here? Anyone, pick one. Saturn? Saturn, I heard Saturn. Saturn is super-solar in carbon, right? Why is that? We don't know. The Earth has excess deuterium, right? And that tells us actually that Earth's water formed at very cold temperatures. And I could give you a story about any one of these other planets, and it all relates back to birth, okay? In the solar system, we have the ability to look at the main constituents and also the trace species, all right? That's important. And we can look at the minor bodies. When we get to exoplanets, we don't have that luxury. We can detect major compounds, right? And maybe in the future we can observe trace species, but not like what we're detecting in our solar system. And of course, minor bodies are not possible. So then how do we make a connection? How do we study exoplanets, chemistry in our solar system, and connect the two? And the way to do that is, one way to do that is by a bulk composition. So this is a plot of the equilibrium of a planetary atmosphere. So you have pressure and temperature. Here's Jupiter, okay? So you're getting deeper in Jupiter, okay? So this is the surface. And what's shown here, you can't see it, this is where the carbon would be in equilibrium. So equilibrium chemistry, my favorite definition is if you waited, it's the way everything would go to if you waited forever in a day. Well, in Jupiter, that's probably like 10 seconds, right? Because the pressures are so high. And what that means is if I'm down here with Jupiter, if I provided carbon in any form, it would go to methane. Okay, so when I look at methane, I'm looking at carbon, and I'm tracing the bulk abundance. Right? At least that's the idea. Okay, so if we can look at bulk abundances, maybe we can tease out something of this story. All right, so for giant planets, this is something that we're doing right now, and I'm going to talk about this at the end of my talk, and then Ilse will pick up a little bit further about what we're doing in astrochemistry. We look at things like the C/O ratio and the total carbon and oxygen content. Terrestrial worlds are a lot harder. Of course, we're not observing them yet in terms of exoplanets, but we have dreams and hopes, right? The atmospheric chemistry may be in disequilibrium. That's absolutely true, but it doesn't matter. If the form that's supplied would be redistributed if it's in the atmosphere, right? And there might be substantial subsurface reservoirs, so we can't probe the bulk content. And so what I show you here, this is really gets at that point, since this talk is going to be about carbon. This is the distribution of carbon in the Earth, and it uses a unit that I have never used before, and I probably will never use again, gigatons. And if we just look in the biosphere, so the biosphere has about 2,400 gigatons of carbon. Well, actually, we believe that there's some carbon in the core, and as you can see, it's 4 by 10 to the 9th gigatons. So there's carbon in the Earth, but it's not on the surface, or so we think. We actually don't know if it's that value in the core. That's just an estimate. So there is a substantial subsurface reservoir of carbon on our planet. All right, so I'm going to take a very broad view and start from the beginning in the interstellar medium, look at where carbon is, and then go into the planet-forming zones and talk about comets and asteroids, and try then to connect to planets. And in this case, the planet that I want to talk to is the Earth, because we think the carbon did something here because we're standing here, right? So for the interstellar medium, that sort of sets the beginning. So where is carbon in the interstellar medium? This is Barnard 68. We've seen that. It's a beautiful picture of nothing, which actually is something. It's got enough mass in there that's hidden to make at least a star and probably some planets. So we know that 50% of elemental carbon in the interstellar medium is some sort of refractory form. And what I mean by refractory, it means that its sublimation temperature is high enough that it's not going to be go into the vapor state. So 400, 1,000 Kelvin, and we're talking about regions that are 10 or 20 Kelvin. Okay, so 50% of the carbon is in this carbonaceous dust, and of course all of the silicon is in silicate dust. And 50% of the carbon resides in CO, which is much more volatile. It has a sublimation temperature about 17 K at interstellar pressures. So why do we care about this? Because these refractory solids are the seeds of terrestrial planets, right? These tiny things got together and had a really big party in protoplanetary disks, and a bajillion of them made the Earth. But we're not sitting on a carbon rock. We're sitting on a silicate rock. So let me back this out for you. So to do that, I'm going to continue, and we'll look at comets. They're born much greater distances from the star, colder, okay? And there's two samples that we have sort of estimates of bulk content. There's Halley. There's the Rosetta Comet, which is stuff is coming in. And then there's so-called sun grazers. I don't know if you can see it, but there's two comets here that are coming close to the star, and they get completely ablated. In that thing, there was a little explosion there. It actually is a coronal mass ejection, has nothing to do with the comets. But the comets get completely ablated, and we have these telescopes sitting there to observe the sun, and they can measure the total content. And then there's meteorites. So they form somewhere of 3 astronomical units. 1 astronomical unit is an Earth-Sun distance. So there's the most primitive type of meteorites, the least altered, and then there's other forms that are more altered. I'll talk about these for a second, because these are really neat. So carbonaceous chondrites. This is a plot of the CI chondrite abundance of all kinds of elements versus the solar photosphere. And what you'll observe here is that there's this straight line. That's what we mean by these things being unaltered. All right? So that is these primitive rocks have the same abundance of most elements as the sun does. In fact, this is so accurate that if we can't measure something in the sun, they ask what is the abundance in a CI chondrite. But there are discursions from this trend, and these discursions are very, very meaningful. Right? If I look down here, the sun is depleted in lithium. That's because lithium is destroyed in the sun when it was young. All right? These are the noble gases. They're unreactive. They're not in rocks. They're not in gas. They're in the gas, and they don't get into the CI chondrites because they're not in the rocks. Right? And, well, interesting enough, here's carbon. It deviates off the trend. So does nitrogen. Oxygen's also a little bit off. And, of course, hydrogen is incredibly volatile. So it's a neat little story just in and of itself. So the final thing that we'll try and pull all this together is the Earth. And the geochemists use this term called the bulk silicate Earth. So it's the entire Earth, including the fluid envelopes, the atmosphere and the oceans, minus the core. So it's the silicate part of the Earth. So here it is. This is carbon versus over silicon going from the beginning to the end state. All right? So let's just back this out here. So half of the carbon in interstellar medium is in some sort of refractory solid form. That refractory solid form is reflected in comet Halley. not in these sun grazers. It actually is also reflected in the Rosetta comet. And that is just about half or a little bit more or whatever than what the sun has. So that makes sense. But it's not in the meteoritic material. And the Earth is way down here. So perspective is, the Earth got one carbon atom in 10,000 that was available. It's an incredibly inefficient process. But yet we're here. Right? And if we'd gotten more carbon, who knows whether we would be here, right? Or if we got less. Of course, we don't know the answer to that. But what it's saying is whatever this thing is something's happening here. This interstellar dust is somehow getting destroyed before it gets into the precursor materials of the Earth, as measured by meteorites, and something else happens during planet formation. Okay, so we have the story of Earth formation, and maybe terrestrial worlds writ large, is a story of massive, massive carbon loss. So the first step is destroying these interstellar grains, right? And so how can they be destroyed? So for that, I just want to go a little bit to the physical perspective, and gratefully you've had some talks before that gave some more of that perspective. So this is a disk here. So this is height. This is distance from the star. Okay, we know that the disks are flared. We actually observe that, so they capture more stellar radiation than they otherwise would if they were flat. So the starlight is being absorbed on the surface. The surface is hot. The midplane is cold. All right, so that's the realm of the ices. And of course, it's hotter closer to the star and colder further away. So there's two gradients. And what this is all set by is through the radiation transfer. So this is a model I'm going to show you of the radiation transfer of UV light that is impinging on the surface. So this is I'm going to show you a movie of photons moving around in a 3D space on a 2D plane. So you're going to see the lines do interesting things. But what you're seeing is the UV photons are coming in and they're scattering and they're getting deeper penetration in the disk by having multiple scattering events. And it's this radiation that is providing some of the heat for the surface and, of course, close to the star itself. And this is an example of some of the modeling that we do. Actual, you get the assumed optical properties of the materials in the disk, so interstellar silicates or interstellar carbonaceous grains, and then we run very detailed Monte Carlo radiation transfer codes, and then back out what the UV radiation field is, the temperature, and so on and so forth. Okay, so I know it's hot on the surface and hot closer to the star. So, how can we destroy these things? Well, one possibility is sublimation. That is, it's hot enough that the grains are just destroyed. So if it's 500, if the sublimation temperature of carbonaceous material is say 400 K, and it's warmer than that at the Earth's radius, then we wouldn't be sitting on a carbon rock, right? We'd be sitting on a silicate rock, because silicate would survive up to 1300 K or 1600 K. All right, so that's one way of avoiding being on a carbon rock. Another way is, well, maybe we can combust things. We can oxidize them. Or we can photoablate them. And we looked at this using combustion chemistry. We found out that this doesn't work. And so we're back to try and figure out how sublimation works. And that's the problem is we know that there's carbonaceous grains. We don't exactly know what it's composed of. So you have to assume or think of or kind of try to constrain what the sublimation temperature is before we can go further. And that's where we are now, and we have some good ideas that we're working down. But, for astronomy, if we're in the inner solar system, the carbon's not in the rocks, it's got to be in the gas. All right? And we're going to have this amazing space telescope that's going to launch called the James Webb Space Telescope. It will be sensitive to vibrational modes of a whole bunch of molecules that arise from hot gas. Where is the hot gas? Close to the star, in the terrestrial planet forming zone. So this is a predicted spectrum that you might observe from James Webb towards a sun-like star. This is wavelength and flux, and so the red stuff here, this is water, orange, ammonia, This is CO2 Q branch here. There's the green here is OH, which is scattered through the spectrum. There's methane somewhere over here, and C2H2. So we can look and see whether there's any of this excess material and see if we can capture Earth's without carbon being born. Okay, well that's one step, right? We have to remove the carbon from the precursor materials to the rock, to the Earth. So the precursor rocks that are going to make the Earth, that's measured by meteorites. Now we have to ask, well, what happens when you go from meteorites to the Earth? And there, it's been quite the journey for me. And the neat thing is when the Earth is getting bombarded, right, there's lots of energy being supplied, it enters a molten phase. We know that molten phase existed. The Earth is differentiated, right? The iron is in the core, and we have a lighter silicate mantle, right? So we know the Earth entered this molten phase. If carbon is present when iron is still not differentiated to the core, it will react with carbon and take carbon with it. And we know that there's a light element in the Earth's core. We just don't know whether it's carbon. For geochemists, it could be anything short of silicon. It could even be hydrogen. But there's a possibility that it's carbon, and that's one way you could do it. But we, of course, want carbon on the surface of a terrestrial world. And that could be provided by providing so much carbon that the iron can't take it all away. Or the carbon could be supplied via an impact after the Earth is solidified, so-called late delivery. But however we want to shake this sort of really suggests, if you look at this writ large, that the presence of carbon on the surface is not preordained. And furthermore, whatever's going on, there probably is likely a range of outcomes that might be possible, and even the possibility that there could be worlds that have significantly more carbon than the Earth does. All right, so for my last part of the talk, I just want to sag to giant planets. Good. Okay, so there we want to look at the C/O ratio. So the idea we have there is you have core accretion, that you form a giant planet, many Earth-sized core, and that gets large enough to gravitationally capture gas from the nebula. And in its simplest form, the core is basically the solids, right? And the envelope should reflect the composition of the gas at birth, right? So if we want to think about our carriers of carbon and oxygen, we know that there's the refractory carbon, and there's oxygen in silicates. Or there's volatiles. These would be in the solid, in the core. The volatiles are the thing that might potentially be in the gas. So CO and CO2 for carbon, water, CO and CO2 for oxygen. So if we think of a disk, here the disk is hot and cold going out here, there would be a series of sublimation fronts where you have, say, CO would sublimate at this distance because its sublimation temperature, so this is laboratory measurements I'm going to show over here. This is the CO laboratory measured sublimation temperature. And this is shown as a function of pressure, or if you want to think of radius. And this is one model of a pressure temperature profile in a disk. So we would say that the CO ice line, if you will, the vapor to ice transition would be at 30 AU. And water, of course, is much more bonding to the surface. Its ice line would be much closer. So let's add all these things together. So I have a disk. The major ice lines for the volatiles would be CO, CO2, and water. And the solids we don't even worry about because, beyond the water ice line, the refractory material is all in the solids. So here I am. I'm in this disk. I'm inside the CO ice line. The CO is in the gas. The water and the CO2 are on the dust. That means if a giant planet is born here at birth, its C/O ratio would be unity. That giant planet could then move, perhaps, and we know that they can do that, but it may carry this signature throughout its entire evolution. That we don't know, but that's a possibility. So that's something that we're doing today. And if you go to the CO2, inside the CO2 ice line, you would get a different C/O ratio, and a planet born in here would have the same ratio as the sun. So this is a simulated spectrum of what James Webb might do, and this is something that the exoplanet community is doing today, and I'm not the expert. The experts are here. You're going to hear from them. But we can measure the main constituents, carbon and CO2, that are expected to carry the carbon in equilibrium. And with James Webb, you can get very high accuracy, or so this paper claims, on the C/O ratio in the exoplanet. This is the claim of what you could do today with Hubble, and this is what we can do in the future. Okay, so bulk abundance, I think, are an important tool that we have, and our planet has information on its own history. And I think, if we can get an understanding of how the fate of this interstellar carbonaceous material, and then maybe we start making predictive models of what the distribution of Earth-like worlds might be in terms of their carbon content. And then you could take models of evolution to figure out what's surface and what's subsurface and so on. But we can maybe then try to link to observations even of terrestrial worlds. But we are certainly doing this today, and this is an emerging subfield. And we have this amazing journey ahead of us. This is a really, really exciting time in this field. And I'll leave you with this picture, which you can't do it justice with this lighting, that shows the chemical effects as a function of star formation. This is a molecular cloud. This is what Els was talking about, a photodissociation, a UV irradiated region. There's B68. There's an outflow. This is a binary, and this is a disk. And all these things show chemical effects. Thank you so much. Because the silicon just sticks around and doesn't do anything, but the carbon is being destroyed. So, you could do whatever you want. You could reframe it that way. But the carbon is so important for life, and silicon's not, right? And so the Earth is carbon poor by that standard, but clearly rich enough to have life. So I think it's a semantics. No, the sun probably has about, probably has a fair amount of the silicon that might exist. You remember as the disk is transporting material inwards, the small grains that are, say, 10 microns or 100 microns inside, they're tied to the gas, and they're accreting inwards and being supplied. So the sun is getting a constant supply of solid material along with the gas. It's possible that there's a slight deficit because we have planets here, and there is some silicate in the material, but the sun has probably, in a relative sense, the about amount of silicon that was present in the system when it was born.
Other questions? So when we're talking about bulk abundances and you're talking about meteorites, are you talking about meteorites that have fallen on Earth, so we're assuming from our own solar system, or do you assume that that's the same for every planetary system?
Right. So I'm talking about meteorites that we've collected on the Earth that are samples of maybe 50 or so major bodies that banged into each other at some point in the past. It's not a representative sample. It's just whatever reached the Earth. However, in white dwarf atmospheres, they're thought to be completely hydrogen helium dominated, and there's good reasons to see that. And in the atmospheres, they actually see evidence for carbon and iron that shouldn't be there. And we now believe that that's due to basically asteroids and things being completely torn apart and then falling on the surface of the white dwarf. And the rocks that they see there, are carbon depleted, hinting that this is a universal process in planet formation, which is really like, whoa, okay. But that's the amazing beauty of astronomy.
At what distance from the sun would you think that if a terrestrial planet formed, it would have a relatively higher abundance of carbon such that it wouldn't be destroyed.
I wish I knew the answer to that, but certainly greater than 5 AU. I think it's pretty clear to me that the Kuiper Belt and the Oort cloud, they're just gigantic carbon silicon rocks, right? Which I think they are.
Do any of the large moons in the outer solar system have any
They might
relevance?
bear some information, but if they formed in a hot accretion disk, I don't. Yeah, it's interesting, right?
You'd briefly talked in the early part of your presentation about the deuteration of the water on Earth.
Yeah.
Is there anything more in because you touched that briefly, and I'm trying to connect to the morning
Yeah,
as well.
sure.
Is there anything further that we could use from the different isotopes of carbon, nitrogen, et cetera, to complement kind of the ladder of what you presented here? Is there anything based on isotopes that would strengthen some of
Oh,
what you presented?
absolutely, absolutely. So the isotopic signature is a real clue that we can use as a fingerprint to try and trace back source materials. And for example, as Paula noted, the D to H ratio of asteroids as sampled by these primitive meteorites is comparable to the Earth's oceans. And dynamic models suggest that it's easier to bring material that's closer to the Earth to supply to the Earth than it would be from the outer solar system, although it's not entirely 100%, but that's more likely. That same material that has the water signature also has carbon and is bringing carbon at the same time. So you can look at the nitrogen signature, you can look for noble gases, and so yes, I think that is the future, is to go, we need more samples from the asteroid belt, maybe with some sample return missions or missions that fly out there with very sensitive mass spectrometers to so-called main belt comets that are evaporating material. We can measure that. Fly through Saturn's Enceladus plume, right, and do all kinds of things and try to bring everything together. It's really every tool in the chemical toolbox will relate to this.
Other questions? All right, let's thank Ted again.